Well, hello everyone. This is KP the Math G, and I do appreciate you tuning in. Whenever you do tune in, it's morning here, and I'm so appreciative of you, and appreciate the God-given ability that has been given me to do this, and hopefully I will do the job that will be pleasing and satisfying to you and will help you. That's what my goal is to help you. And basically I want to keep this calculus based right now, and then maybe if there's other things I can do to prepare people for calculus, such as Algebra 2 and Pre-Cal, and maybe even college algebra, I'll be more than happy to do that. But anyway, we want to talk a little bit about the mean value theorem. And actually in that we get into a discussion of Rolle's theorem. I'm just going to abbreviate there. And I want to talk about that first. They're kind of together in this. Rolle's theorem has to do primarily with, let me just say, maybe where you have something like this, maybe, okay, and I don't know, okay, so here is A and here is B, and of course the slope here is the same here, but there is, if F at A, there's a rule that says if F at A, which in this case is 0, equals F at B, then surely there is a C somewhere right in here, okay, somewhere right in here, such that F prime at C is equal to 0. Between, and we have to specify this very closely. It's on the closed interval A to B, but differential on the open interval from A to B. Okay, differentiable. If it's differentiable, one thing we do know is that it is continuous, albeit not everything that is continuous is differentiable. For example, this picture right here, X and Y, this picture right here, as you probably have seen before, this is definitely continuous, but not at all differentiable. So we want it, if we say continuous, doesn't necessarily mean differentiable, but if we say differentiable, we do immediately mean that it is continuous. So I'll tell you, I'm already having trouble with my there's my other magnet, and so it comes out every once in a while. But anyway, let's get back to this discussion right here. There is a horizontal tangent line right here, okay, right there. Alright, so there is a horizontal tangent line between A and B, where, so that's what we're talking about, where F prime at C is equal to 0. And that's what we're talking about here. Okay. That is Rolle's theorem, and kind of an offshoot of the mean value theorem, which we'll get into a little bit later. Let's do an example of Rolle's theorem, and this gives you the idea of what we're talking about here. So let's go ahead and dive into Rolle's theorem first. There is a difference between Rolle's theorem. Rolle's theorem primarily is about the horizontal tangent, whereas the mean value theorem is more about you can have a tangent, line, as long it doesn't necessarily have to be a horizontal tangent. Rolle's theorem, yeah, you have to have a horizontal tangent, but the mean value, the slope of the tangent line can be anywhere. And you're comparing a tangent line to a secant line there. So let's look at this Rolle's theorem. There's a couple of examples that I could look at, but let's say that we have f at x. F at x is equal to sine x, or sine, well, we're going to have to say x. If we say x here, we've got to say x here. And it is on the closed interval 0 to 2 pi. We're going to make it from 0 to 2 pi. Okay, I could have very easily made this from 0 to pi or something like that, or moved it somewhere else. But anyway, we want our interval to be there. And if you notice, or if you recall from time past, the graph of sine goes from -1 to 1, and remember, here's 0, pi over 2, pi, 3 pi over 2, and 2 pi. And here's Rolle's theorem. This is the idea. Okay, the graph of sine, let me get a different color. Maybe we can see it that way. Okay, bear with me right now as we are going through this problem. But it's going to go up, down, down, and up. And notice that throughout that from 0 to 2 pi, that definitely that f at 0 equals f at 2 pi, which is equal to 0. So that's the first thing you need to do, is test that. So we're saying then that f at 0 is 0, and f at 2 pi is also 0. That's the first thing you need to check. They need not to be different. Then now we need to find all the c's. There's at least one c, and I should make that clear, at least one. It could be just one, but there's at least one. So that f at c is equal to 0. So here's what we're doing here. So we had the test here. F at 0 is equal to 0. Certainly we know that sine of 0 is 0, and sine of 2 pi is also equal to 0. That's what I mean by that. Okay, alright, so even looking at the graph, you can easily see that. That's what we're looking at here. Alright, now the next thing we need to do is take f prime and set it equal to 0. So f prime at x, the derivative of sine. Anybody know what the derivative of sine is? Yeah, okay, cosine. So let me finish here. Okay, cosine of x. Now cosine of x is equal to 0. Well, where is cosine x equal to 0? Well, let's look at it. Let's look at the graph of cosine. And, as a matter of fact, what we can do is just transpose it right here. We'll just look at cosine. is in blue. Alright, it starts up here, comes down here, comes down here to -1, back up to 0, then back up to 1. So let's see, cosine of 0 here and here. So let's see, right here at pi over 2, and doesn't get to 0 again until 3 pi over 2. And this is the two places. If you think about it, if you look at the y value, look at that, that's going to produce a horizontal tangent at pi over 2, and then another horizontal tangent at 3 pi over 2. That's what Rolle's theorem is about. Alright, so x equals pi over 2 and x equals 3 pi over 2. And of course they must be also between 0 and 2 pi. They must be in the open interval of 0 and 2 pi, and certainly we see that pi over 2 and 3 pi over 2 is between 0 and 2 pi. That needs to be established right there. So, okay, that is an example of Rolle's theorem. Okay, that if F at A equals F at B, okay, then there should be, and of course F must be differentiable, which means that it is continuous. We got a smooth curve instead of a cusp or something like that. It's not disjointed or anything, and so we can see then that we do have somewhere between 0 and 2 pi at least one horizontal tangent. This is where the slope is equal to 0. And that's why we set F prime is this. That's why we set it equal to 0, so we can get that horizontal tangent. Okay. I'm sure there are applications to Rolle's theorem, but this will suffice for now, just to give you the basic idea. Alright, let's look at the mean-value theorem. Okay, let's look at that. As a matter of fact, probably we can let's just flip our board over, what do you say? And we'll start on the mean-value theorem. Alright, now, okay, the mean-value theorem simply is something like this, maybe. Okay, so we are into the mean-value theorem. MVT is what we generally call that. And what it means is that the slope of the secant line, okay, which by the way is F at B minus F at A over B minus A, that slope is equal to the slope of the tangent line, which is F prime at some letter C. Okay, there is a C between. We can guarantee that there, and of course, again, it's differentiable, which means that not only is it differentiable, we find the derivative of it, but that means automatically that it is continuous. Differentiable and continuous. Alright, on some interval, in this case, on the, we talk about the closed interval, but differentiable on the open interval, A, B. There is some C between A and B, and maybe the picture will look, so if you have a picture that looks maybe something like this, and you have, oh, I don't know, you have a curve like this, and here is a, okay, so here's a secant line, here's A, and then right here is B, and you have a secant line right here between A and B, and not like this. Okay, then according to the mean value theorem, there is a C somewhere between A and B. There exists a C so that the slope of the tangent line is equal to the slope of the secant line. So, okay. So the slope of this is the slope of the secant line right here. Okay. This is actually, if you think about it, rise over run, y2 minus y1 over x2 minus x1. That's what that is there. Okay, this is, okay, the slope of the tangent line right here. Okay, okay. Parallel lines, right? The slopes should be parallel to each other. So that point C is somewhere right in here, maybe. Okay, that's the general idea. Pictorially, that's a good way to see that as far as, and there's so many applications to this mean value theorem. So that's kind of the idea there. All right, and again, it does not have to be a horizontal slope, as you can tell. Mean value theorem takes care of those other slopes as well. All right, so that is that as far as the illustration goes. Okay, so let's do an example, and maybe in another video I will give you a probably an application type problem, but I just want to do something like this. Let's take this problem right here. All right, and it does not really matter. I'm just going to go ahead with this one. Okay, so let's say L at x is equal to 1/3 x squared plus 2. We're on the closed interval from -1 to 3. Okay. All right, and then we want to find a C. Let's just put it over here. Let's erase this up here. Okay. I want to have plenty of room up here. Excuse me, I'm going to turn my heater off. I've got a smaller heater in here. I had to exchange heaters. I had a bigger heater in here, and I put it in the greenhouse. I've got a big greenhouse, so it needed a bigger heater. It's got more volume to heat up, and so this one has less volume in this room. So, oh, it's warm in here now. So yeah, this little heater is working fine. Okay, so what we want to do is we want to find a C. All right, and in -1 in the open interval. All right, that satisfies okay, this theorem right here, this idea that satisfies the conditions of the mean value theorem. Okay, here's our problem that we're going to look at, and we're going to first, well, we can do either one first. We can find L at C and see where that is. But let's do this now. L at B So here is A and here is B right here, guys and girls, and whoever else may be watching. Alright, so F at B, we're looking at F at 3 minus F at -1 over 3 minus -1. That's what we're looking at. So let's do that. Oh, okay, so on the side I'm going to do F at 3, 3, and that's going to be 1/3 times 3 squared plus 2. I do have that squared, don't I? Yeah, okay, plus 2. Okay. 3 squared is 9. 1/3 of 9 is 3. So 3 plus 2 is equal to 5. Alright, there's the 5 up here. So we have 5 minus, okay, now F at -1. F at -1 is going to be, okay, so let's see, 1/3. Hold on just a second, bear with me please. 1/3 -1 squared plus 2. Okay, that's it. So -1 squared is 1, but 1/3 times 1 is 1/3 plus 2. And here's something you need to look at. This is actually 2 and 1/3 then. 2 plus 1/3, or 1/3 plus 2 is 2 1/3. That's what it is. And then if you want to write this, this is 2 times 3 is 6, and 1 is 7. So 7 over 3 right there. So that's what I have there. It's going to be 5 minus 7 over 3. And then this is minus a minus, which is plus. It's over 4. Like that. Okay. I want to make this 5 a denominator of 3. So I can say 5 over 1 times 3, and 3 times 5 is 15. So 15 over 3, that's where the 5 comes from. So I'm going to go ahead and just say 15 over 3. Okay, I'll just go ahead, 3 times 5 is 15, and then put that over 3 like that. Minus 7/3, and then divided by 4. Okay, so now, right now, we're just working on the secant line. So the slope of the secant line, what is it? Okay, so, alright, so let's see. This is 8 over 3 divided by 4. So 8 over 3 divided by 4 is 8 over 3 times 1 over 4. And notice 4 goes into 8 2 times. So this is equal to 2/3. So the slope of the secant line is 2/3. Okay, the slope of the secant line is 2/3. So let me do a little erasing here. And okay, so this was, we know it's 2/3, remember that? So all this equals 2/3. Alright, so equals 2/3. Okay, so now what we have now, according to the mean value theorem, is that the secant line, the slope of the tangent line needs to be equal to the slope of the secant line, and it needs to lie within the open interval (-1, 3). Okay, so 2/3. Alright, so let's see. So this is equal to 2/3. Now f prime at c, let's find that. F prime, well, we're going to find f prime at x, and we'll substitute c in place of that. Okay, so let's see, this is, we're looking at this right here, we're looking at f prime at x. So let's see, 2 times 1/3 x, remember the derivative of a constant is 0. This is 2/3, so f prime at x is equal to 2/3. See, 2 times 1 is 2, 1 times 3 is 3, 2/3 x. So this is the slope of the tangent line. It's equal to the slope of the secant line, and it so happens that this is the same. That's nice, because I know what the value of x is, don't you? Just by looking at that. If I multiply both sides by 3/2, that's going to get rid of my 2's and 3's, and I'm left with x on this side. Multiply this by 3/2 here, and again, 6/6 is 1. And 1 is definitely between the open interval -1 and 3. I'm saying that if we get even -1 or 3 or even -2 or 4, we can't use that, okay? Because we want this to be in this open interval here, and we wait until we find the final answer to do that. So yeah, 1 is between -1 and 3, and so we can guarantee you that at x equals, this is the slope, okay, it's equal to this slope here, 2/3, at x equals 1, that's what the slope is going to be, okay? Alright, the slope of the tangent line there, okay? Alright, so that is what we have decided to do today. I promised my wife I would make a fairly quick lesson. I hope this has been. So hopefully, by seeing the picture and kind of getting the idea, think of this as the slope of the secant line. This is the slope of the tangent line, and the number that we find must fall within this open interval, okay? Going back to Rolle's theorem, we said that F at A equals F at B, alright? And so that simply means that we need to find a C, at least one C, so that a C between A and B, such that that slope is a horizontal slope there. So anyway, we found that this slope is not equal to 0. It was equal to 2/3. So the slope of the secant line is 2/3. The slope of the tangent line is also 2/3. It's equal to that 2/3, and that's what you do there. Alright. There are more problems that are a little more to this. If this is x cubed and then you got an x squared or something like that, then you may have a trinomial that you need to factor, and so on like that. So anyway, that's the difference between Rolle's theorem and the mean value theorem, and this gives you the idea here. And again, signing off is KP the Math G. I hope and trust that you have a very wonderful day. Thank you so much for listening. Hit the subscribe button there. Don't forget to do that. And again, I trust that you'll have a very, very good day, and Lord willing, a very good and prosperous Thanksgiving. Thank you so much.